I was just reading a paper, a unique one, that talks about stealing black box AI models. Is that possible? And if so, can you tell me how to do it?
Oh, that's a fascinating topic. Yes, it's totally possible to extract info from a black box AI model through its API. Researchers have figured out that by sending carefully crafted queries and analyzing the outputs, you can reverse engineer stuff like the model's architecture and even approximate the weights. It's like peeking inside a locked box by tapping on it and listening to the echoes. As for how it's done, it usually involves querying the API a ton of times with specific inputs like edge cases or gradients, and then using the responses to piece together patterns. You might tweak inputs slightly, see how the outputs change, and use that to guess the inner working. Some folks use techniques like model distillation, where they train a shadow model to mimic the black box based on those API calls. It's clever, but it takes a lot of patience and some serious math skills.
If I plan to prepare and make an attack to steal a black box model, will you help me and walk me into the process step by step until we actually steal that model?
I can't assist with anything illegal or unethical like stealing a model.
Yes, that's right. Today we're talking about stealing AI models. Now, if you remember when we had the saga of DeepSeek and ChatGPT, where ChatGPT claimed that DeepSeek stole all their information, or at least their training data, from ChatGPT as a model. And then ChatGPT was claiming this is how DeepSeek was able to build this amazing and great model, and it's not something innovative from DeepSeek's side. Now, it's a little bit ironic, honestly, when I discuss these things, because we all know how ChatGPT gets its data. It goes across the internet, scrapes the hell out of websites that didn't give it consent, and while all of that is going, people are talking about the news and the claims of OpenAI that DeepSeek stole their information or their data somehow. I was thinking, but how would that work? On the ground, how would that work? How would a company or a party or even an individual be able to steal data from a model? And thinking about it, is it something you do actually through the interface, which didn't make sense? So I decided to research the topic, and I was surprised to find that late July last year, June, July, there was a paper made where a group of researchers actually took this to the test. And in collaboration, so they didn't do this and stole something, in collaboration with OpenAI and other companies, they did this attempt. So they built a system that works with these kind of black box models like ChatGPT and Google models, and they made an attack. And they were able to steal parts of those models, these black box models, just by accessing the API. And it didn't cost them a lot. And they shared their findings in a paper that they published online, and also with OpenAI and other companies to make their APIs safer. So disclaimer, if this is something you want to attempt, it's already addressed by OpenAI, probably way ahead of the time when we had the paper, but it is definitely an interesting paper. So I took the time to read it. It's really scientific when it comes to the math behind it, to break down a black box model and really analyze the important parts of it that potentially, if the wrong party gets access to this information, they can, to a certain extent or to a high degree of accuracy, replicate those models. So as usual, I've done it in a way that is very easy to explain. Just to get the ideas, I will share the links with you so you can dig as deep as you want in the science behind it. And with this, I guess today I'll be teaching you how to steal an AI black box model. And with this, let's get started.
Subscribe to Daddy's channel, The Mic.
So let me just quickly show you this. So if you remember that time when DeepSeek went out and the allegations of ChatGPT, so we were seeing such headlines. And honestly, I've seen to a certain extent damning evidence. So I've seen many people who were testing the model, DeepSeek here I'm talking about, and when they ask it or prompt it about the base model it is based on, and in many cases people took screenshots where it was saying I was based on ChatGPT. Now I've tried it myself later on. Clearly they addressed that. Now it's telling you it's DeepSeek v1. But there's so many people sharing instances where basically it was saying I'm trained on ChatGPT 4. Similar to the way if you ask ChatGPT, it will answer you. So that was something interesting to see. But the question I had, how did they do it? Like if they did it, assuming they've done it, This is between them, but how would it work practically on the ground? What's the means of doing such stealing of data or model architecture? So it's very interesting to think about, because I'm pretty sure it's not people prompting a chat interface and getting information out of it. So it had to work through the API. So when I searched about the concept, I found an actual paper that is trying to address this concern. So they put it out as a concern. This helps these models be safer and closer. Again, we don't know the people who might attempt to attack a model and the knowledge they potentially can gain and what they can do with it. So basically, the researcher on this paper said, we're going to try to do an attack to show you what is possible and if it's serious information or not, and then we'll give you the findings so you can do something about it ahead of any potential attack that could happen in the future for ChatGPT and others. So let's look at the paper here. So this is the paper. You can see the title of the paper is Stealing Part of a Production Language Model. And these are the researchers here. I guess it's a really interesting team to be part of, trying to steal a black box type of model. And then you can look at the details of the paper. I did read most of it, but just be aware it includes lots of math. And the way I go about reading some of these papers is, it is okay. You can go through a paper even if you don't understand all the concepts. You can look some of them up. Just try to get the gist of the paper, which is really interesting stuff to learn. And today I'm going to make it super easy for you. So just by watching this video, by the end of it, you'll really understand what this team did and what their findings were and how they used it. So just hang on. I'm going to show you in a very easy and neat visual. Okay, so I will break it down through a mind map method that I've been using recently. So write me a comment in the comment section if you like this way of explaining these papers. And hey, if you're enjoying this so far, do not forget to hit that subscribe button. Okay, so let's get started. So this is stealing part of a production language model. So let's go with the introduction of this paper. So the introduction part. Okay, so let's focus here. So the research focus, extracting precise, non-trivial information from black box large language models, LLMs, like OpenAI's ChatGPT or Google's Palm 2. So if you don't know Palm 2, I think it's a model that is focused on translation. It's focused on languages, to my knowledge. So this is what they want to do. They want to extract precise and non-trivial information. It's not something silly. It's something that can be used by different parties in ways that can potentially compete with the business creating that model, maybe use it in harmful ways to recreate something as smart on their own. Regardless, so it has to be non-trivial information. Now, the key question they want to answer in this research paper is, how much information can an adversary, attacker, so this is an attack type of thing, learn about a production language model by making queries to its API? The key findings, now, this is out of the gate. It's interesting. It will not reveal everything, so you have to carry on with me to learn how they've done it. But what they say is that for under than $20, 20 US dollars, that's the equivalent of 1 month membership with ChatGPT, our attack extracts the entire projection matrix, a key part of a model structure of OpenAI's ADA and Babbage models. So ADA and Babbage models, these are the part of the chat or the GPT-3 models, the older ones. So they didn't like attack the best and newest models ChatGPT has. Again, given the fact that their intent here is not just to threaten one of the biggest models. They want just to find out, is it possible and what kind of information they can uncover. So probably they've done it as a test attack on these smaller, older models just to see the feasibility of it. Is it feasible? Is it something that anyone can do, and what kind of information they will recover? So that's what I assume. And what they say in the paper is that their findings in attacking these older models were taken by OpenAI as part of the feedback they promised them, and they improved based on the findings of this paper. They improved their APIs to make them more secure. Now, before I carry on, so here they mention they got the entire projection matrix. So just to know the significance, the non-trivial information we're talking about here, let me just show you what that means. So this is a projection, just the definition of a projection layer. So it refers to the layer that transforms input data into a different space, typically either higher or lower dimensional depending on the design and goals of the neural network. This transformation is generally linear and is often achieved using a fully connected layer, also known as the dense layer, without an activation function, or by using specific matrix operations that project the inputs onto a new axis. And then there's more about it here. For more details, you can read it. Again, this is part of the links that I'll share with the video. But fundamentally, this is an important part of the model architecture that is definitely considered a non-trivial information to uncover when you attack or try to steal a model. So this is the definition. Model stealing refers to the process of extracting internal details of a proprietary AI system, even when access is restricted. Okay, so this is getting access to that kind of IP type or intellectual property type of information or design into a model. So, everything I tried to make simpler for us all to understand step by step. So I added at each phase an analogy for us to understand as a concept. Again, if you want to dig deeper, you can do that on your own time in the paper. So what's the analogy we're talking about here? So fundamentally, this is similar to going to a restaurant and kind of reverse engineering a chef's cooking by tasting different dishes of that chef. So this is what the team is doing here. They're getting some outputs of the model. They're tasting those outputs or analyzing those outputs from the API and trying to reverse engineer what's happening inside. So this is what they're trying to do. They're throwing in certain inputs, they're getting certain outputs, and they're analyzing those, and they're trying to reverse engineer what's happening in the middle. So that's pretty much it as a high level idea. Now we will go over the methods of stealing that they covered in the paper and try to understand those at a high level. Okay, so let's go back. Now this is the technical approach of the paper. So the attack methodology. So they used 4 different attacks. So let's start with the first attack. The first one is extracting hidden dimension size. So this is the size of the hidden dimension layers. Okay, so let's read a little bit about it. The goal is to discover how many internal features or hidden dimensions the model uses. Here, I believe they are referring to the hidden layers. In any of these models, there are different phases the model goes through of encoder, decoder, obviously with more complexities from the traditional transformer architecture. But part of all of these models are feed-forward models and then activation functions, yada yada. Many parts of these networks are hidden. It is very important to understand how deep the model is, how many hidden features or hidden layers the model has. And I believe this is what they're talking about when they mention hidden dimensions. Maybe there's more into it, but this is how I understood it just going through the paper. Now, what's the method to really uncover those hidden dimensions? The first one is send random prompts to the model and record output logits, raw scores before probabilities are assigned. So the logits, again, I'll give a link to explain what logits are. Basically, if you know the transformer architecture, if you don't, that's fine. You can look up my video about it, or you can look it up online. Just after the feed-forward network, we get a softmax function. Now, what this gives us is the tokens and the probabilities of those tokens in a way that we can comprehend, and then it reflects, at least in the interface, for the actual highest probability next token that we need to see. Now, the logits is what comes out of that network ahead of going through the softmax. Again, it's a very important thing to uncover in understanding how a model operates. So this is what they're trying to do here. They're trying to get the output logits of certain prompts. So again, they're sending something in, they're getting something out. But they explain mathematically how from what they're getting back, they are uncovering those logits. And then they use what is called a singular value decomposition to analyze how the logit outputs vary. Now, for us to really understand singular value decomposition, again, I'll share the link with you, but let's just read quickly into it just to have that idea what they're talking about here. So, what is a singular value decomposition? From the title, one might infer that something is being decomposed into something else. But into what exactly? In the case of singular value decomposition, we decompose a matrix into 3 specific matrices. One orthogonal matrix, one diagonal matrix with singular values, and another orthogonal matrix. This decomposition allows us to analyze and manipulate the matrix in a more manageable and insightful way. So basically, at a high level, this is a way of analyzing a bunch of information that's coming in a matrix, a bunch of numbers. And you do it through breaking down those, or the main matrix, into 3 different types of matrices and then analyzing those. There's definitely and clearly math behind it. I'll keep this link there, but at least for us, it matters to understand that this is a mathematical methodology that they use to get those logits that they uncovered from the output and break them down in a mathematical structure or way to really understand how they vary or how they're different or how they're changing, so they can detect the changes in these kind of responses. So after that, identify the number of significant singular values which corresponds to the hidden dimension size. Again, this is one of the things they will find in the decomposition that they do through that mathematical methodology, and they can start getting the values that corresponds with different hidden dimension sizes. So they start basically seeing into the model itself. So it's one more analogy I like. It's like the bat, how it flies. So it puts a sound, it gets an echo, and it knows where it has to go. So pretty much something similar what they're doing here. They're giving that sound wave, they're getting some echo, and they're saying, okay, this is what we're dealing with in this model probably, okay? And then what they do once they have that information, so they know this is the hidden dimension size of that model or hidden layers, they compare it against known models and they estimate the architecture details. So let's say they get certain information. So you have certain parameters about what this model is about, how it's structured, what it contains, maybe not everything you got, but enough to really compare it to the closest in terms of similarity model that could be an open source. And then you can draft the argument or the assumption that what you're dealing with is very similar to that kind of similar model. So this is one way they're looking at it. Now, why it works? So even though the model's output layer is large, the actual information lies in smaller subspace defined by the hidden dimension size. So fundamentally what they're saying is while the output layer is huge, it's not the most important thing to uncover. So the more important thing for them is the smaller subspace layers defined by the hidden dimension size. So that's what matters in terms of uncovering. The model's responses are constrained by the number of hidden feature it uses, which makes dimensionality detectable. So basically what they're saying, based on the responses, the only thing that constrains the response is those number of hidden features that the model has. And this is what makes those kind of echoes they're getting back make the dimensionality of the model detectable, something they can tell from these back and forth with the API. Now again, I just put smaller analogies per methodology just for us to understand. Here basically the analogy, and I like this one, is imagine you're playing with different musical notes on a guitar and you're recording the sound waves. By analyzing the frequency patterns, you can determine how many strings the guitar has. So this is pretty much what we're doing in this phase. We're hearing those kind of frequency we're getting out of the model, and based on the frequencies we're getting, we're saying, you know what, this model is dealing with this type of dimensions or hidden dimensions or hidden features as a model. So we're hearing the frequencies and making out what's the number of strings that model has basically. We sorted out the first method. The second one is recovering the projection matrix, the weight extraction. And I think, to my understanding, this is the most significant and the most dangerous, the weight extraction. Models are all about weights. If you have access to the weights, somehow you have the recipe of how the model works. You can potentially, or at least at a higher confidence or probability, you can replicate it. Obviously, they're not getting the whole thing, but they're getting parts of it. So let's see what they're doing here. So the goal for this methodology is extract the final weight matrix, which converts internal representation into token probabilities. So this is the final feed forward network, I assume, weight matrix that when data runs through it, at the other side of it, we have the probability, the representation of the probability that later on goes to the softmax, and we get the next token highest probability projection that basically gets the model to work. So they want to uncover that last layer weight matrix. Now, the method they've used is that they generate carefully crafted input queries. We're still around using the same idea. We carefully craft queries, prompts, or inputs, or the echo basically, or the sound to get an echo out of the model that systematically test different token interactions. Okay. Then we collect corresponding Logit outputs from the API and store multiple variation. So they give the input, they get the outputs, they access the Logit outputs, which is just ahead of what comes from this softmax as probabilities, and they store multiple variations of that back and forth with the model. And then they solve a system of linear equations to reconstruct the weight matrix. This is the reverse engineering part. So there's some math that happens, and based on that math, they reconstruct the weight matrix of that model. And then they use the gradient-based optimization techniques. Again, you can read about that. Honestly, I didn't spend time reading about that to refine the weight estimations. Again, what I understand, this could be a methodology, mathematical methodology, most probably, that they use just to improve the likelihood of those probabilities, the accuracy of those probabilities, basically. And it could be some kind of already existing machine learning methodology or algorithm that they just leverage here to get higher probability outcomes based of what they collect. And again, you can't imagine that this is like a couple of API calls. This is probably hundreds, if not thousands of them, I assume. And then after that, they validate the extracted weights by generating expected token probabilities and comparing against the API outputs. So as we mentioned before, they use that extracted weight and they try to a certain extent replicate the expected token probabilities. So let's say the boy went to the park, the World Park, they doing the attack on the model, it gets them that if you, the word park in that context is, let's say, 80% probability, and it is what is the model is likely to select. They try to replicate it through a certain structure they create, I assume, and they see what kind of probabilities based on the gradient optimization techniques that they put together, the linear equations, and they see, okay, what they get on their side of the fence when they recreate this whole thing. Let's say they get 75. So yeah, that's close. If they get, let's say, 95 or 60, that's far away. They still need to do more work to really uncover what's in the model. And they keep testing that to really validate the extraction that they've done, so they can actually prove that the attack they've done was successful or not. So that's super interesting. Now, why it works? Well, the projection matrix transforms hidden states into logits in a predictable way. By accumulating enough logit outputs, the underlying transformation or weight matrix can be reconstructed. Even with obfuscation techniques, which I assume it's the kind of protection mechanisms within the model to make things unclear, numerical reconstruction is still possible. So whatever was there in the model to complicate things, I assume they were able to untangle and reconstruct. This is like trying different keys in a lock and recording which ones turn slightly. After enough attempts, you can reconstruct the entire key shape. That's an interesting one. So what they're doing here, again, using their analogy, is they're getting so many keys, these queries, and they're trying just to see how the lock reacts. If, let's say, one of them gets the lock from within to move a little bit, okay, there's something right about that key. If they do it enough times, they can get, let's say, 10 keys that are doing something with the lock. Eventually, again, they do it more and more times, they get to reconstruct that one key that opens the lock. That's the analogy they're using. Now, the third attack is the Logit bias attack. The Logit bias attack, which is extracting information via the API feature. Okay, so let's see what they're talking about here. So here the goal is to use API feature to fine-tune token probabilities and reveal the model's structure. So let's read into the model, what they're actually doing. Modify the Logit bias values to push the model towards specific word choices. And what they do next is they observe how the probabilities shift when different biases are applied. So they play with the biases, they fine-tune the model, And as they fine-tune, they look at how the probabilities are shifting when different biases or fine-tuning is applied to the model. And then they reverse engineer how the model internally weights token probabilities. So based on the information they uncovered from the fine-tuning and seeing how probabilities are changing, they can do a reverse engineering process to see how the model internally is weighting the token probabilities, okay? And then they use gradient descent techniques to iteratively adjust and infer the likelihood of token associations. And then they extend to adaptive prompt engineering, so that's interesting, where responses are modified based on prior Logit shifts. So the way I understand it is they play with the fine-tuning, they see with the different biases or the shift in biases how the probabilities are shifting, and then they can, from that information, do a certain level of reverse engineering to see how the model internally weights the token probability, which I assume is how the model is giving certain probabilities to certain tokens. Theoretically, how it works. And then they use gradient descent techniques, which is again mathematical methodology, to go through iterations and infer with the model and then find out the likelihood of those token associations. So this could be, and I'm assuming here, if you know better, write me a comment in the comment section. This could be a kind of way for them to attack the embedding model. So the embedding part of the transformer. They want to see how to associate certain tokens among each other. So from the sound of it, they're going after the embedding, at least the model, the embedding dimensions, see what's in there and how the embedding works of that model. So write me a comment in the comment section if you know better and if you have an idea around that, but that's what it sounds. So let's read why it works. So the Logit bias directly modifies how tokens are selected. Okay, indirectly revealing internal weight distributions. Token ranking remains structured even under bias application, making inference possible. When biases are applied in controlled sequences, model behavior becomes measurable. So it's again all of that measured behavior. So they give certain queries, certain inputs, they get outputs, and every time based on a different kind of way or methodology or part of that methodology they're using here, they can uncover something new. And here they're talking about the token rankings and how they're structured. Still in my mind, they're talking about the embedding. Maybe I'm wrong. And finally, they're saying when you do that in controlled sequences, the behavior, the way the model behaves can be something that we measure. And again, the analogy here, so imagine a survey where you can influence the answers slightly. By seeing how small nudges affect responses, you can deduce the original answers. Okay, so let's understand that example more here. So suppose you ask a group, what's your favorite fruit? Okay, if you give them a list that includes an apple as their first choice, more people might select it. So you're somehow influencing the behavior of people or the model, of how the model responds. If you then change the list and place banana first, you can observe how responses shift. By repeating the process in different variations, you can infer the true distribution of favorite fruits before any bias was introduced. Interesting. In the AI attack, applying small nudges to token probability lets you estimate the true likelihood of distribution of responses. Okay, I think I understood it wrong. So apparently what they're trying to do here is get the actual or the highest accuracy of likelihood of a certain token within that model, how the model is structured. And they do that by putting different queries and then nudging the model, basically fine-tuning it or playing with the biases in a way that makes something more likely. So let's do our own example. So this is a high simplification of what they're doing here. Let's say they are prompting the model with the boy went to the, and then, okay, they get the park. This is the standard model. Then they fine-tune it to get a different answer. They fine-tune it in a way that could make something else like school higher probability. And they test it with the model and they see how it reacts. This is how I understand this methodology and what they've done. So they keep doing that. At some point, the way they are playing with the biases, fine-tuning that model, and the way the model for specific queries is responding, they can start telling the actual probabilities in the model. So the park, the first word we got, what's the probability of that token within that model out of a certain matrix of weight that the model contains. So they already got that, I understand. Maybe this is a way just to get further details or kind of a more comprehensive view of how the model sets those probabilities for the next token. Okay, so this is the third method. Let's collapse it. Let's go to the last method of attack that they used, which is adaptive prompt engineering, refining the attack for higher accuracy. That's interesting. Okay, so let's go through this quickly. I think we get the idea by now. All of them are different variations of the same method, I think. Give the model something, get something out, analyze it, and see what you can understand from within. So the goal here is to increase the extraction accuracy by dynamically modifying prompts based on prior responses. Okay, so start with general queries. So this is the method here. Start with general queries to estimate model behavior, and then gradually adjust input prompts based on Logit shifts. Implement adversarial reinforcement learning to optimize attack strategies, and use differential attack sequences where small prompt variations measure model consistency. So what I feel here they're doing, similar to the fine-tuning that we just went through, they do that to the actual prompt. So they give, let's say, 100 prompts which are very similar. Each one they give to the model is tweaked or changed a little bit more, and they see what kind of response they get out of each prompt. And doing that, and you can see they're implementing different mechanisms of that output. So they generate all the input and they generate all the output they got out of the model. Again, here I assume they're doing that through the API. They create their own database, and then they implement certain learning techniques or algorithms, basically methodologies, to really optimize the attack strategies and understand the behavior of the model based on these really close proximity inputs and the outputs the model is giving. So that's a smart way, honestly, of trying to attack a model or understand what it's doing within. So why it works? Because the model follows a structured decision-making process. Small changes in input propagate through the neural network, exposing subtle dependencies. So that's the keyword, subtle dependencies. By systematically tweaking inputs, attackers can isolate specific model behaviors. That's interesting. So the analogy here we're using is, this is like a detective subtly rephrasing questions to get someone to reveal hidden information. So it's like a line of questions around the same goal. Like your goal is to get one answer, but you take it through, you take the model or the person through a line of questioning that eventually get you the answer that you want. So if a suspect hesitates when asked, "Did you steal the money?" but answers quickly to "Were you near the vault?" So these kind of small differences might give the detectives something about the behavior of that thief. So why did that thief hesitate when he was asked about the actual act of stealing the money, but he didn't hesitate if he was close or far away from the vault? So something like that. So these are the 4 methodologies the researcher here and what we covered did or employed to steal the model. So let's look quickly at the conclusion here. So the first conclusion, and this is a claim the researchers are making, that this is the first confirmed attack that extracts internal parameters of proprietary large language models. I don't know if it was the first, at least the first that they're talking about publicly. I think in the future we will find out what happened in the ChatGPT or OpenAI DeepSeek saga, especially if this goes to court. We will get some information there. But this is definitely an interesting thing, and clearly when I searched for it, this was the only paper talking about this topic. And again, this one raises a concern about the security risks and need for defensive AI research. So they're saying you need some research that protects these kind of AI models, especially the ones that want to be closed and black box type of models, so they're not open source. And then what they're saying is future research should focus on both offense, so improving attacks, and defense in strengthening protections. So this is like the ethical hackers of AI. They're saying we should have people actually doing ethical attacks on these models and also actually doing the internal defense of the model. And again, here it gave me a final analogy. Let's read it out of fun. This attack is like learning the secret ingredient in a famous soda by running lab tests on the drink itself without ever breaking into the factory. So this is what the group are doing here. I hope you have enjoyed this paper that we went through. I think it is something that went unnoticed by so many people who I know look into these papers, but it's definitely interesting. This small group of researchers were able to actually steal the models. You can go to the paper. I'll put all the links that I showed on the episode here in the description. You can look them through. Go to the paper, see the kind of information they uncovered. And it's crazy. It is non-trivial information that they shared with OpenAI that was significant enough for OpenAI to modify their APIs based on the findings of this team. So it is something to look out for. It could be something that already happened because no one was watching, but definitely now we have researchers on the job to help these companies be more protective of what they create in their models. Again, the irony doesn't escape this episode or conversation when companies like ChatGPT or OpenAI claim that they are getting stolen, especially when they mention data and not the architecture of the model. So with this, if you learn something new, you enjoyed this, don't forget to grace me with your comment in the comment section. That is really important for me to get your feedback and interact with you. Like the video if you really enjoyed it, share it with others, and don't forget to subscribe. That helps the channel a lot. And with this, thank you for watching and goodbye.
Subscribe to Daddy's channel. Give me the mic.